In this last lecture of chapter 41, we're going to turn our attention to another case, and that is the so-called unbound or scattering state. This is where the particle has enough energy to reach positive and negative infinity, which happens when the total energy E of the particle is greater than the value of the potential energy at positive or negative infinity. So the particle being able to go all the way to positive negative infinity is no longer trapped, it is no longer bound. Now in the case of bound state, we learned that we apply the right boundary conditions, we will arrive at the quantization of energy. So the quantization of energy was the result of satisfying boundary conditions. So what about the unbound state? Do we still apply the same boundary condition to get the quantization of energy? Well, let's take a look. Let's look at our first example. This, in fact, is problem number 59 in the textbook. It's called the quantum step. There are two cases for the quantum step. In each case, you have a zero potential, and then the potential rises abruptly by a step to a value u0, extending all the way to infinity. But the first case is when the total energy of the particle is higher than the potential step. So E is greater than u0, which we'll study first. And next, we'll also study the case when E is less than u0. Well, in either case, the particle at x equals negative infinity, the energy of the particle E is greater than u because u is 0 over there. So the particle starts from negative infinity. Okay, remember, it is no longer trapped at a finite region. It starts out from negative infinity. It is therefore a traveling wave. We can express it in terms of a traveling wave function e to the I kx minus omega t with a constant a in front of it, which represents amplitude. And it comes in like this. What happens when a wave keeps on traveling? If there is no potential change, k will not change, so it keeps on going. It's just a pure state of momentum. But when it hits this step, it's just like a medium has a change, so the wave goes from one medium to another. Even in classical physics, we know what happens. Part of the wave gets reflected, another part gets transmitted, right? It's just like light going from air into glass, for example. You have reflection and you have transmission. So you have a reflected wave. So here is the wave that's reflected, like this. I can write it in terms of e to the I negative kx minus omega t, right? Because it travels backwards. And the coefficient in front of it, I call it b. So that represents the amplitude of reflected wave. And yet another part of the wave gets into the step. And that is e to the I k, or I should have kappa x minus omega t. Well, in fact, let me change the symbols. Here I call it k1. That's also k1. And here I call it k2. Okay, I do not call it kappa here anymore. Call it k2. And the coefficient in front of transmitted wave is c. And there is no reflected wave from positive infinity, of course, because it keeps on going and never changes. The potential never changes, so there is no reflection anymore. So using the boundary conditions at positive and negative infinity, I know there is a wave coming in, and part of it get reflected, but there is no wave reflecting back from infinity. Okay, so that makes sense. So I'm dealing with traveling wave instead of standing waves. And the question remains, is energy still conserved? Is energy still quantized in this case? Well, let's see. Let's see if it makes sense to have a quantized energy, which means, does it make sense to have energy assuming only a certain number of possibilities, certain number of values? Well, think about it. I have a quantum step here. That's at x equals 0, right? But a particle starts from x equals negative infinity. It's way down there. When you start from there, would you even know that there is a quantum step here waiting for you? Of course not, right? It keeps on going, and you hit this quantum step, and then part of it gets reflected. Now, when you start from there, you have a certain amount of energy. You have no idea at the time that there is a quantum step of certain height waiting for you, and therefore, you're just a free particle over there until you hit this snag. And there is no reason why this quantum step would affect something at infinite far away, because you don't see the quantum step at all. And therefore, at infinite far away, there is no potential And it's just a free particle. A free particle can have energy, whatever value it wants, right? So just from this common sense, we know you really shouldn't quantize energy here anymore, because this E energy, or K1, is really based on the initial condition when the particle just gets started, and that's where it does not see that potential at all. Now this is different from the case of bound state, because in a bound state the particle does not go to infinity, okay, and therefore it doesn't it's trapped in a finite region close to the potential change. Therefore the potential will actually help define the energy of the system. So therefore it's meaningful to have quantization of energy there, but not in our case. That is our hunch. Let's actually solve this problem to see whether energy indeed is not quantized. Let's see that. So again, let's write down the Schrödinger's equation for this quantum step as we did before for the bound state. It is a piecewise constant potential just like before, so kinetic energy equals total energy minus potential energy, and total energy minus U is just total energy for x less than 0. There is no potential there. And for x greater than 0, E minus U naught. Remember, E is greater than U naught, so this is a positive number. Okay, this is a positive number. And I move to m over h bar squared over to the other side. I define K1 and K2 just like before. Both K1 and K2 are real numbers because their squared value is greater than 0. And so the general solution would be a traveling wave, okay, e to the positive negative I kx. You notice I didn't use sine or cosine because sine and cosine are standing waves. I want to use a traveling wave, so e to the positive negative I kx. Positive means it travels along the positive x direction. Negative means it goes backwards. And this is when you add the time dependency, you can see more clearly that this is indeed a traveling wave. Positive, that's when x goes positive, travels along the positive direction. Negative sign means as time progresses, x becomes smaller and smaller, it goes backwards. Now, I need to satisfy the boundary conditions at x equals positive and negative infinity. And again, that means that you comes in at negative infinity, there's a wave coming in, and the wave gets reflected at x equal to 0, and only the wave gets transmitted after x gets greater than 0. There's no reflection anymore. So you have the incident wave, a reflected wave, and then a transmitted wave. Okay, there are three coefficients here, A, B, and C, reflecting the amplitudes. Now, how many unknowns do we have here? We have three unknowns, A, B, C, and of course, we don't know the energy. Once we know the energy, K1 and K2 are both fixed. So we have actually four unknowns, A, B, C, and E. Let's see whether we have enough equations to uniquely find out all these four numbers. If we could, just like we did before for the bound state, that would mean energy cannot assume just any value. It must be fixed based on these equations. Then we would have quantization of energy just like before. But is that true, that we have enough equations? Well, we have the boundary condition. We already considered boundary condition at x equal to positive negative infinity. Therefore, for example, we never had a wave going backwards from bouncing off from x equals positive infinity, right? So the only boundary conditions left are the ones at the quantum step, x equal to 0. So x equal to 0, you have the quantum step right here. So here you have A coming in, B coming out, and C, B reflected and C coming out. And therefore, at x equal to 0, because the wave has to be continuous, you set x equal to 0, x equal to 0, x equal to 0 here, you get one condition. And then also, the first derivative of psi also has to be continuous at x equal to 0 because it has to be smooth. U is not equal to infinity there. That will give you two equations, right? One for x, one for psi, the other for d psi over dx. That is only two equations. I have four unknowns. Okay, so you say, oh, what about normalization condition? And that is normalization, right? Well, in the past, we were able to normalize the wave function because the integration never actually extends to infinity because psi there would be 0 anyway. But can we still do it here? Can we normalize this wave function? And the answer, unfortunately, is no. Because we're using the exponential function, not the sine cosine function to describe this wave. For example, this is the transmitted wave, right? Just look at, let's only look at x greater than 0. So we have to use this wave. And the integral goes from 0 to positive infinity, right? You take the absolute value, modulus squared. The modulus squared of this exponential function equals 1, okay? It's a constant, right? And then the integrand equals 1, going from 0 to infinity, you get infinity. What did that tell us? It tells us that in this particular case, this traveling wave, the normalization condition is not satisfied. It is not equal to 1. And this sounds strange, but it's actually not a surprise if you think really hard about it. Okay? This particle, unlike the bound state, can go all the way to infinity. Therefore, the chance of finding it everywhere in space is extremely low because it's so spread out. The wave function spreads all the way to infinity with a constant amplitude, c. Okay? When you can be found anywhere, I mean, with an infinite range, the coefficient c must go to 0, right? But when the coefficient goes to 0, you got nothing left. And therefore, because of the extent of the wave function, it cannot be normalized. It cannot be normalized. You don't have the third condition, normalization condition. But we have 4 unknowns. You know what that tells us? Just as we suspected, it is now impossible to fix the energy E as a function of all these things that m, h bar, whatever, or u naught. And therefore, indeed, as we suspected, for this continuous, unbound state, the energy is not quantized. It is not discrete, rather it's continuous. Energy E can assume any value you want. You just throw a particle at this quantum step. Depending on how hard you throw it, you give this particle whatever energy it possesses. That is your freedom. The system cannot dictate the energy anymore. It is a continuous spectrum of energy instead of a discrete spectrum. Okay, this is for the scattering or unbound state. Quantization of energy is not an absolute requirement in quantum mechanics. Energy is sometimes quantized, sometimes not quantized. So, we cannot fix energy, so what do we do for this particular case? Well, we still have a lot of things we can learn from this quantum step, so let's see. If you apply the boundary conditions at x equal to 0, that's the edge of the potential step, you have these two equations, and that will lead you to these two. Okay, when you apply the expression for psi 1 and psi 2, that's what you're going to get. Here is just a plus b equals c. Here is when you take the derivative of both sides and set them equal, you get that. So you see, we have 3 unknowns, a, b, and c, but only 2 equations. This allows us to find b over a and c over a, but not a, b, c all together. And you know what? That makes perfect sense. You know what a means? A is the amplitude of the incoming wave, right? Now, if I increase the number of particles flowing in, okay, I have a stronger flow of particles, then A increases. But when A increases, B also increases, C also increases, everything increases, the ratio stays the same. It is the ratio that I'm really concerned about, and that is out of the incoming particles, every 100 particles coming in, for example, how many particles gets reflected, how many particles tunnels into the second medium, and so on. Those are the things I'm interested in. Okay, I don't really care about the absolute values of A, B, C. I just care about the ratio. Okay, by the way, you can calculate B over A and C over A from these 2 equations, and that's what you got. Very simple algebra. Okay, now let us look at the issue of particle flow rate. We define what's called particle flow rate. What does that mean? It means the number of particles passing through a certain region of x, certain value of x per unit time. Okay, let's do that. Let's say here's the x direction. Okay, here's the x direction. And let's say I install a gate of cross-sectional area A. And I want to figure out, I want to measure how many particles would pass through this gate of cross-sectional area A during the time dt. Okay, let's call this number of particles dn. Then dn over dt is the rate at which particles flow through this cross-section, right? Now, the particles that are trapped within this volume region will all pass through this gate over time dt. And the length of this box is v dt. V is the speed of the particle. So if a particle has a speed v, then after time dt, it is barely able to make it across this gate. Okay, if it's further than that, then with a speed v, it cannot make it anymore. So all I have to do really is to count the number of particles already inside that box. All these particles will pass through this gate dt in a time dt. So how many particles are there? Well, that depends on two things. That depends on the volume of the box, which is v dt times a. It also depends on how many particles per unit volume, n. Okay, so if n times dv, dv is the volume here, that would be dn, right? In divided by dt, that's dn over dt, the flow rate. Okay, so dv, the volume, is v dt times a, so a v dt. Okay, so cross out dt, you get n a v. This n, forget about a. Okay, a is just a unit, it's cross-section area. I can just define it to be 1 unit, so just n times v. And this n is the number of particles per unit volume trapped inside the box, and that is proportional to what? To the probability density, right? Probability per unit volume of finding the particle there, which in turn is, by definition, psi squared, right? The wave function squared, that is dn, dp over dn. Okay, what about this v? V is the speed of the particle, which is proportional to the wave vector, actually proportional to momentum, which is proportional to the wave vector, k. So dn dt is some sort of constant times psi squared times k. Now, I don't care about that constant because I don't really care about dn dt per se. I care about the ratio of dn dt for the incoming wave, for the reflected wave, and for the transmitted wave. Okay, I want to know how many particles go through, how many particles get reflected, and so on. So we know there is a basic requirement for the conservation of particles. This is how many particles flow in, okay? Out of these particles, per second, okay? Part of these particles will reflect, that's reflected. Part of these particles will be transmitted, and clearly, by conservation of particle, I would have to have the rate of particle coming in equals the rate of particle getting reflected plus the rate of particle getting transmitted. That is conservation. Now, we know that dn dt is proportional to psi squared k. Okay, and psi squared, psi is the exponential function times what? Times that a or b or c, right? So basically, it's just a squared for the incoming wave. Isn't the amplitude like a squared, right? Because the exponential part, e to the I, whatever you take the absolute value, that's 1. So that's a squared times k. K is equal to k1 for the incoming wave, and here's the reflected wave. For the reflected wave, the amplitude is squared is b squared. And for the reflected wave, it's also back in the first medium, so k is still k1. Right? For the transmitted wave, the amplitude squared is c squared, and it's in the second medium where k equals k2. So this is equivalent to that. Okay. Now, if I divide everything by this thing here, divide every term by this thing here, then what do I get here? This term is basically the particle flow rate of reflected wave divided by the particle flow rate of the incoming wave. That is called reflection coefficient. Okay? Again, the flow rate of reflected wave divided by the flow rate incoming wave, that in fact tells you what is the percentage of the particles getting reflected. That's R, reflection coefficient. And what about that one? That one is the flow rate of the particle getting transmitted divided by the flow rate of the particle coming in, and that is called transmission coefficient. Basically, it tells you what percentage of particles are actually getting transmitted. So this side is 1, so therefore this is R, this is T. By conservation of particle, we should find T plus R equals 1. I put a question mark because we haven't tested that yet. Okay, but clearly that should be the case, right? Because of conservation of particles. Now, is that true? Well, let's see here. We know what A, B, C's are. In fact, we know what the ratios are, B over A and C over A right here. Let's test that. Let's put our ratio of A and B into the expression. Okay, B over A equal to this. C, so T equals this. I just plug in B over A and C over A. And you take a good look. Okay, the denominators are the same for both T and R. It's K1 plus K2 then squared. The numerator for T is 4K1 squared times K2 over K1. That's 4K1 K2. For the R, it's just K2 minus K1 squared. Now, if you add them together, what do you get? Same denominator. The numerator is K2 minus K1 squared, and then plus 4K1 K2, right? That is the same as K1 squared plus K2 squared minus 2K1 K2 plus 4K1 K2. So the cross term is now plus 4 1 K2, 4 minus 2. So it is 2K1 K2 positive. And therefore the numerator now becomes K1 plus K2 squared, canceling with the denominator, and indeed you get 1. Perfect. Okay, that means that indeed Schrödinger's equation is consistent with conservation of particles, as it should be, because it is correct. Okay, so that makes sense. And you see here, if K1 equals K2, what does that mean? It means there is no such a step, right? U equal to 0. So the particle keeps on going, keeps on going. Will it ever be reflected upon hitting the step? No, because there's no step to talk about. Okay, so in that case, by physics, we know R should go to 0, nothing gets reflected, T should be 100%. That's indeed true, because when K1 equals K2, look at R. R is 0, right? K1 equals K2, and T is 100%. That is a special case, that makes sense. But given the values of E, the energy, and the potential step U, you can find K1 and K2, and from that you can find the percent of the chance the particle getting reflected, and the percent chance it gets transmitted. Okay, so that was our first example. We learned from this example that in the unbound or scattering state, the energy is no longer quantized. It is no longer a discrete energy spectrum. Rather, it's what's called a continuous energy spectrum. We also learned that the solution satisfies the conservation of particles. All right, now our second example is the same quantum step, but with a different energy. The incoming particle now has an energy that is lower than the potential step. Okay, so classically, when it hits here, it's got no place to go but to bounce back. It does not have enough energy to get anywhere into the second region. It is classically forbidden. Quantum mechanically, what happens? Well, we know that incoming wave will be partly reflected. That's certainly true. But does that mean that nothing gets into the second region? Well, that is not true, because even in a bound state case, we learned that was not true. Remember the simple harmonic potential, right? The particle can actually go into classical forbidden region for the ground state, for example, because it's all the way from negative positive infinity. It does go into classically forbidden region. Okay, so the question is, what do we do here? We have seen the math in a finite potential well. The particles do have a chance to go into the classically forbidden region. It's just it is an exponentially decaying function instead of an oscillating function. And here is the math. The math is quite simple, as we've seen before. In x less than 0, it is an oscillation. Okay, this is where u equals 0. At x greater 0, we have to use kappa, not k. And kappa, you have to put u naught ahead of e because u naught is greater than e. So kappa squared is a real number. Kappa is a real number. But you don't have a negative sign here anymore. Okay, so clearly the solution is different. Here you have this is a traveling wave solution, and this is an exponentially decaying solution. In fact, you can have e to the positive negative kappa x from math point of view only. Okay. But we must satisfy the boundary condition at x equals positive negative infinity. And this is what happens if you apply the boundary condition at positive infinity. You have a wave coming in, okay, amplitude A, and that wave gets reflected upon hitting the barrier. So you have a B coming back. Okay, this is the wave coming back, reflected wave. But when you apply the boundary condition at x equals positive infinity, you find that certainly you need to discard this solution of e to the positive kappa x, because that will go to infinity at x equals infinity, making no sense. Okay, so you have to only keep this. Okay, so we have already satisfied the boundary conditions at positive and negative infinity. Now, we still need to satisfy the boundary condition at x equal to 0, where the step rises. Okay, so just like before, continuity of the wave, continuity of its first derivative, and you plug in this and plug in this, you do the derivatives, and set x equal to 0, and this is what you can get. Now, an interesting difference here is that there is an I here that you didn't have before. There is an I here, okay, unlike our first example. So A, B, C, again, I can find C over A and B over A. Let's find B over A first, and that's what we get. It's kappa plus IK divided by kappa minus ik, and with a negative sign. Simple algebra. Now, what is the physics here? The physics is that, unlike the previous case, the particle, the wave function, decays exponentially upon getting into the second medium. Right? The wave function looks like this. Right? It is no longer oscillating. And therefore, the chance of finding this particle diminishes as you try to get deeper and you get deeper and deeper into the well, into the potential barrier. The particle has no chance to go to infinity anymore. So if a particle comes in, part of the, it may have a little chance to go in, but then it diminishes, the chance diminishes. Eventually, what happens to the particle? It comes back. It comes back home, okay? It cannot go to infinity anymore. And therefore, we suspect that the reflection ratio should be 100% this time. Because the particle, again, cannot possibly escape to infinity. It's got no place to go but to get reflected. Is that true? Is R really equal to 1? Well, let's see. R is B over A, absolute value squared. And here is B over A. Then we take modulus squared. Modulus squared is equal to this complex number times its complex conjugate, right? So k minus ik times the complex conjugate, and that is k plus ik. Here, you do the same thing. Take this times its complex conjugate, which is k kappa minus ik. And clearly, these numerator and denominator cancel out, and you get 1. That's exactly what you should expect from physics. Okay, so now I have 100% reflection, because eventually no particle ever goes to infinity. Everything should go back. Okay, very good. Now, let's take a closer look at what happens when a particle makes its way into the second medium. The wave function decays exponentially, right? So what is the chance of finding this particle? What is the relative chance of finding this particle at a certain distance x into the barrier? Well, that is the wave function is e to the negative kappa x. The probability density goes like wave function squared, so it goes like e to the negative 2 kappa x. Okay, it is an exponentially decaying function of x. And how fast does it decay? Well, let's see here. If x equals to 1 over kappa, we have a special name for it. We call it delta, so-called penetration depth. At x equals 1 over kappa. Kappa times x equals 1, right? This is where this whole exponential function goes to e to the negative 1, and you square it for the probability density divided by its value at x equal to 0, which is 1. Okay, this is 1 at x equal to 0. You get e to the power negative 1 squared. E to the power negative 1 squared, if you do the algebra, it's about 13.5%. It's roughly 1/10 of the incoming, of the probability here. So there is about only a 10% chance the particle can go this far, okay, compared with here. And that's pretty small. So we say, roughly speaking, the particles, once they hit this border, they only go into this medium for about this far into the medium. And then they have very little chance of going any further beyond, and they will be turned back. Okay, as a matter of fact, since the probability of finding this particle goes exponentially down as x increases, we can do a little exercise to see how fast the probability decays. This is when x equals delta, right? I mean, it's not terrible. It's actually a little over 10%. You can find it there. But what about 10 delta? What about 10 delta? When x equals 10 delta, right, the ratio is no longer e to the negative 1, but e to the negative 10, right? And then you square it, that's e to the negative 20. E to the negative 20 is 2 in a billion. So there's only a 2 in a billion chance the particle can go 10 delta away from the origin. So that is how fast the probability decays when the particle tries to get into the second medium. So you see, classically, no particle gets in whatsoever. Quantum mechanically, yes, the particle still has a finite chance of going in, but roughly speaking, it can only go about this far, okay, about this far into the second medium. That's called penetration depth. Let's take a closer look at the values of the penetration depth. The penetration depth, 1 over kappa, okay, and kappa is equal to this, right? U naught minus E. Okay, U naught minus E. H bar over 2m. You see here, the penetration depth, that's a unique quantum phenomenon. In classical physics, the penetration depth is 0, okay? So the more quantum the system is, the greater the penetration depth. And in classical physics, when you take this thing going back to classical physics, delta should approach zero because there is no such thing as penetration into classically forbidden region. Let's see. One way to take delta, one way to take back to classical physics is when you make m very large. Okay, so you're no longer looking at microscopic world, just macroscopic, large m. Clearly, large m means delta approaches zero. That totally makes sense. Another thing is h bar. When you take h bar to zero, everything go back to what? Classical physics, right? And indeed that's true as well. See, because h bar is proportional to delta. When you take h bar to zero, so does delta. Another thing is it also depends on how much the potential barrier is taller than the energy. Okay, if the potential barrier is not a whole lot taller than the energy itself, you don't have to. Yes, you are going to the classical forbidden region, but it's barely forbidden, right? Because you almost have enough energy going in. Therefore, U naught minus E is smaller and delta is greater. You can go further in. But if you are trying to go into a very tall barrier, then even in quantum mechanics, delta is very small. Okay, because U naught is far greater than E, you don't go very far into it at all, even in quantum mechanics. So this all makes sense. But now let's take a look at some numbers. Let's say we have an electron. Okay, this electron tries to tunnel into a region, tries to get into a region whose potential barrier is higher than its own energy, than electron's own energy by about 1 eV. Okay, by 1 eV. So it has this much energy barrier to tunnel through. And let's see what kind of how far can it get into such a barrier. Okay, so we calculate delta for this case. And again, the same old trick. We're going to multiply both numerator and denominator by c. Okay, so I get h bar c here, and this becomes mc squared instead of m. H bar c is 197 eV nanometers. Remember that? Okay, mc squared is a 511 keV. That's 10 to the 3 eV. The difference between U naught and E is 1 eV, as I said. You tunnel through a barrier that's 1 eV taller than your own energy. You get this ratio. Do the work. Very simple. About 0.2 nanometers. This may not sound much, but remember, the size of an atom is only about 0.1 nanometers. So this is, the electrons actually going quite far in terms of microscopic size, so the tunneling becomes significant. Okay, in the microscopic world, you look at a very large mass, and this is the gap you overcome is no longer eV, but we're talking about joules, and then you can forget about tunneling. This delta is infinitesimally small. There is no such thing as tunneling in the microscopic world. So this is how we study the tunneling effect. It's only significant in the quantum mechanical world, and here is the probability. Relative probability for a particle to go into the second medium, classically forbidden medium, e to the negative kappa x, and this depends exponentially on the value x and on the value kappa. We will see an important application of that after we study these examples.